Hi everyone, my name is Aditi Raghunathan. I am starting as an assistant professor in the computer science department at Carnegie Mellon. I work broadly in machine learning, and in particular, I work on making modern machine learning systems more robust and reliable for real-world deployment. We are at an exciting time in machine learning today, where we've seen some many impressive results over the past decade or so. For example, AlphaGo, GPT-3 with impressive language generation, AlphaFold, and most recently, high-quality image generation as well. Not just these eye-catching impressive results, but machine learning is widely used around us in many different applications, ranging from translation to autonomous driving. My research is motivated by looking at how well do these machine learning systems work in the real world. Here's a headline from 2015 that perhaps a lot of you are familiar with, where it was seen that machine learning systems do not work very well on certain demographics. This issue did receive a lot of attention, and you might hope that things are better now. But a few years later, in 2020 as well, these issues persist, and this time a Black person was wrongly arrested. So I went back and saw what happened in 2015 and how did they address this issue. And turns out that the fix they came up with was to simply remove the word gorilla from their captioning lexicon. So this is clearly not sufficient, and we need more principled solutions to address these issues. Let's look at another domain, self-driving cars. So there's been quite a buzz around self-driving cars and how good are they in practice. So it turns out not so great. And for example, in 2018, a woman was tragically killed where, among other issues, a machine learning model failed to recognize a pedestrian who was jaywalking because it was only trained to recognize pedestrians at crosswalks while it was being trained. So I don't want to start off on a very dark note. So sometimes there are funny errors as well that happen. For example, a football game was ruined because the machine learning model confused the referee's bald head for the football. So what we see is while there are very impressive results that make machine learning an extremely promising technology, but the current machine learning systems are extremely brittle and they make all these errors when we use them in the real world. As we use machine learning more widely around us, a very important question that I'm interested in addressing is how do we make these systems more robust and reliable? So what's the core issue here? Why do we have a mismatch between impressive results and benchmarks at one hand, but also these errors in the real world? So let's look at the standard machine learning pipeline. We collect a data set of examples from some distribution P, and we split this into a train and test set. So we typically train on the training data, and we evaluate on this held out test set, which are examples from the same distribution P as the training data. Most benchmarks as well as theory study this setting, and there are a lot of open questions in this setting as well. But this is insufficient if we think about the real world deployment, because when we deploy a model, it's going to encounter a wide range of examples. In particular, it could encounter examples, for example, pedestrians at jaywalks, which are different from the distribution that it was trained on. So my goal is to make machine learning systems achieve good performance on a large range of examples, including those outside the training distribution P. So to give you a flavor of the kind of examples we look at. So here is a stop sign that a good model would classify correctly. But now we can have these graffiti-like looking black and white stickers that make the model think the stop sign is a speed limit sign instead, though of course humans like you and I will not confuse the stop sign. So you can see how this is quite dangerous for autonomous driving in the real world. Another similar example, you have a sentence that is classified as toxic by a good model. But by just having a small typo, now the model thinks that this content is non-toxic. So it's very easy to subvert content filtering systems based on machine learning if we can just introduce some small typos that change the model's predictions. A really extreme version of this is an example here. So we have an image that looks like a lakeshore that is again correctly classified by a good machine learning model today. But we can change each pixel by a really small amount to get the image at the bottom. So notice that this image at the bottom is basically indistinguishable to the human eye from the image at the top. But the same image will be classified by the model to be a completely different class of a laptop instead. So this shows that even imperceptible changes that we can't even detect can actually completely change the way the model makes its predictions. And so this is really a hard, deep problem in terms of how machine learning models make their predictions, which makes it challenging to make them reliable for the real world. Another kind of problem arises as follows. This is an image of a chest X-ray. And let's say we want to determine if this has a collapsed lung or not. So we can try to train a machine learning model to do so and collect the data set, train a model, and it seems like it works pretty well on the test set. For example, it would correctly classify this image to have a collapsed lung. But if we look more carefully at how the model is making its predictions, we find that actually the way it detected this collapsed lung was to look at this chest drain or this tube over here in the X-ray, which is actually a treatment. So there is a spurious correlation because of the way we collected data, where everyone who was detected to have a collapsed lung also got treatment. And that confuses the model to use the treatment to detect collapsed lung. As a result, the model does not detect untreated collapsed lungs, which are basically the kind of examples we want to use this when we deploy this model in the real world. So spurious correlations in the training data are another big problem faced by machine learning models. So hopefully the goal of robustness makes sense, but why should we study this separately of machine learning? What are the choices that we make when we train a model? We collect some training data, we pick a model architecture, then we put them together and optimize some training objective that leads to the model. And then we finally evaluate these model parameters. So one thing that should naturally change is the training objective, where we try to incorporate some notion of robustness. And most of the work in robust machine learning focuses exclusively on this aspect. But what we find is actually that we need to rethink all parts of this pipeline. For example, evaluation. So when we allow someone to interact and break a machine learning model, that makes the evaluation problem much more challenging, and we need to develop new methods to account for worst case evaluation when we have adversaries in machine learning. Similarly, the way training data and model architecture interact with each other and interact with the training objective also are quite different when we think about robust machine learning versus standard machine learning. In fact, it can turn out to be quite the opposite, as I'll show in a few examples. So a lot of modern machine learning is based on some heuristics and complicated systems that we do not completely understand, and there is some common wisdom for how to train these models that gets passed on. So if we ask a machine learning practitioner whether you should use a large model or a small model, they're going to tell you to use a large model. And in fact, some of the most promising successes that we have today are using large models with many, many millions or billions of parameters. But if you look at robustness, we find quite the opposite, and that sometimes small models, counterintuitively, are actually a lot better and are what we should use if we want to get robustness compared to large models. So here's one example where things are quite the opposite when we try to make it robust. As another example concerning data, we can suppose we have a choice between using the entire training set or just a small fraction. Again, most people would tell you to use the entire training set because more data is always better. But we see that the opposite is actually sometimes true, and maybe training on a subset is actually the better thing to do when we want to improve robustness, which is not the case if we just look at the standard paradigm of machine learning. So these are a few examples to show that we need to rethink all parts of the pipeline and even the basics of how we train machine learning if we were to make it more robust. And the way we try to approach these questions is to have an interplay between both theory and practice. So we start with certain empirical observations concerning what are these mistakes or failure modes that models make. And we try to capture them and understand them in a theory setting and use the simple theory setting to guide us with a solution. And we don't stop there. We try to scale up the solution and actually see that it holds up in practice and addresses these empirical observations of concerning failures that we started off with. So the theory gives us some intuition for what's happening or what causes the errors, and allows us to make hypotheses that we can test by scaling up and seeing. So we try to complete this entire pipeline when trying to address robustness problems that we find in modern machine learning systems. So in terms of the future, if you look at other disciplines, for example, civil engineering, reliability is not an afterthought. We build bridges to be robust and reliable by design. Much the same way, I hope that all of the machine learning that we do is robust, and robust machine learning is actually the standard machine learning in the years to come. Thank you.